examples of graphing the tangent function. So the idea is going to be the same as what we had before. The notes will kind of work the same way. So I'll be erasing or drawing in darker colors throughout the graph. So if you need to add more graphs to your paper, that's fine. So when I see that this is a tangent function, okay, I think of a tangent function of normally having a period of pi. But just like we did with our sine and cosine graphs, this number that's causing any horizontal stretch or compression is going to affect the period of the function. So seeing that it's 3, I would multiply by a factor of 1/3, giving me pi over 3 as the period of the function. So again, I'm going to make the fourth mark pi over 3, more because we've seen this pattern of there's like 4 convenient points for me to mark before I get there. And then if I divide that by 4, I'll have this first mark, so pi over 3 divided by 4 multiplied by 1/4 would be pi over 12. And so then this would be 2 pi over 12 or pi over 6, 3 pi over 12 or pi over 4, and then 4 pi over 12. And then the negative versions of those here. So very similar to how we started sine and cosine graphs, but this graph's going to have a different shape. And it did start with a different period, pi rather than 2 pi. So I like to start with this period of the parent function that is kind of sandwiched between the vertical asymptote that's at the first negative and positive angle. And then the tangent kind of followed this sequence of points like this and had a curved shape like so. So this is basically the parent function, but with this adjusted period of pi over 3. And so the adjustment that I haven't accounted for that's going to change my graph to its final form is 2. So that's a vertical stretch. So even though the tangent kind of middle of the function doesn't look the same as the sine and cosine, that middle point still stays at that place. And then like that this has a distance of 1. 1 times 2 is equal to 2. And it would be in both of these places here. So it just kind of makes it stretch vertically, just like we would explain the transformation with words. So there's my graph. The period is pi over 3. The amplitude for each of the tangent functions is none. It doesn't have an amplitude to measure. It doesn't have a distance between the middle of the function and the maximum, or the middle of the function and the minimum. All right. The domain for the tangent function. So if I continued this, okay, it would go here, here, move this out of the way a little bit. At the next point, it would go up here, and then at the next point, there would be another asymptote. So this is where the domain of the tangent function is more complicated than those that we saw with the sine and the cosine, because it has these places, these x values, where there are asymptotes, meaning that x value, when you plug it in, you cannot calculate the value of the function, so it is a restriction on the domain. It is a number that cannot be part of the domain. So that list, though, because this function continues forever, would be infinite. So it would be something, and then we see a negative pi over 6, a positive pi over 6, and then, goodness, let's see. So that was 12, 2 twelfths, 3 twelfths, 4 twelfths. This would be 5 twelfths, and this would be 6 twelfths, which is like pi over 2. And then this would continue forever also. So what you're going to see is some notation for the domain. So this is a little bit new here, where in order to describe that, instead of writing an infinite list, we write an equation that describes every number that this turns out to be. So notice that it starts at pi over 6, and then the next one is at pi over 2. So the question becomes, how far apart are those? And so, like, what is the distance between these asymptotes here and here? Okay? So how far is it from pi over 6 to pi over 2? So again, these were 12ths, so let's count by 12ths. If I started here, that's 1, 2, 3, 4 twelfths, which is pi over 3. And then let's check here. 1, 2, 3, 4 twelfths. which is pi over 3. So basically, if I start at one asymptote, I'm going to have another asymptote every pi over 3 after that or before it. So you could subtract a pi over 3 or you could add a pi over 3. So what we do to build this equation is we say start at an asymptote. So I'm going to pick pi over 6. And then we're saying you can add or subtract to that any amounts of pi over 3. Okay, if I add pi over 3, I'd end up over here at the next asymptote. If I add pi over 3 again, there would be another one. So basically what we do is we put a little k here, and then we say where k is a part of that set. And if you don't remember this symbol, this means k is any integer. So think about it. You could plug in -2, -1, 0, 1, 2, 3, 4 for k. But what that would really be doing is adding some amount of pi over 3s to pi over 6. Or if k was negative, it would subtract them. But if you subtract them, you end up at another asymptote too. So we're going to write equations like this for our domain. And then the range for the tangent function is going to be all real numbers. We're going to look at one more example. So here's an example. Again, we're going to start with the period. Now this one just has a period adjustment. Okay. And this one, the period stretch or compression here includes pi, so it's going to make it look a little different than what we're used to. So I'm going to multiply pi by the reciprocal of pi over 3, and I'm going to get 3. Okay. That means I'm going to make the fourth mark on my graph equal to 3. And 3 divided by 4 is 3/4. So every mark on my graph is going to be 3/4. So the next one would be 6/4, which reduces to 3 over 2. Okay. The next one would be 9/4, then 12/4, which is 3, so that makes me feel like I did it right. And I'm going to number the same thing this other way. All right. Now, since that's the only transformation, this is going to look like the parent function, but the axis has been renumbered to reflect the stretch or compression that took place here. And remember, we could continue it in each direction. So if this axis continued over here, that same sequence of points. And the same thing would happen in this direction. And if I wanted to see what those numbers were to help me with my asymptotes, remember every mark was 3/4. So here at 3, I was actually at 12/4. So the next one would be 15/4, and then 18/4, which is like 9 over 2. So my period was 3. My amplitude, remember, is none. Okay, and then let's try to write our domain here. So x cannot equal, I'm going to start with 3 halves because that's an asymptote, plus I'm going to add to it how much. Now remember, we were measuring how far it takes to get to the next asymptote. That also happens to be one period of the function. So you could count it here, 1, 2, 3, 4. But you're also going to get every time the same thing you got as the period. So basically, we can add or subtract 3 from 3 halves as many times as we want, and we'll end up at a new asymptote. So I'm going to put 3, and then I'm going to put that k, and I'm going to say where k is included in the integer set. That way, you use either a negative whole number, 0, or a positive whole number. So you're getting 3 over 2 plus another period or minus another period that will help bounce you to each of the asymptotes. And then make sure you ask about this tomorrow if it's confusing for you. And then the range is all real numbers because the graph reaches all those different heights. Okay. If you have any further questions, remember we're going to discuss them in class tomorrow before we're working on the homework. So make sure you enter those at the end of the video and bring those questions with you so we can answer them in class.